So in the last series of videos, we introduced Newton's laws of motion and forces. And now we're going to be taking a look at how to apply those in particular situations. The first class of situations I want to take a look at are what are called equilibrium situations. So a system is said to be in equilibrium if its acceleration is equal to 0. So this means that it's going at a constant velocity. That constant velocity could be 0, but doesn't have to be. Some people differentiate those two situations of velocity equals 0. They'll call that static equilibrium, and velocity not equal to 0, they'll call dynamic equilibrium. But like I touched on in an earlier video about Newton's first law, different observers can disagree about whether an object actually is moving or not. So the distinction is not a huge deal. The important thing to realize is that equilibrium might be a little broader of a definition than you realized, and that includes everything moving at a constant velocity. So the key assumption of equilibrium is that the acceleration is 0. In a few more series of videos, when we get to looking at things rotating, we will also have to require that the angular acceleration be equal to 0, and we'll define that more at that time. But suffice it to say, we'll also have to have the restriction that not only is it moving at a constant velocity, but it's rotating at a constant rate. So with that out of the way, we can start with Newton's second law of motion, which says that the acceleration of an object is equal to the net force applied on it over its mass. And while this is sort of the standard way that most physics equations are written, we usually write them as effect equals cause. This one, just for pure convenience sake, usually people multiply the m through and rewrite it as F net equals ma, just because it's mathematically a little cleaner. And here, and so I'll probably be doing that going forward as well. And here, since the acceleration is 0 as a vector, that means the net force is equal to 0. And this is a vector statement. So what that means is that separately, the x component of the net force has to be equal to 0, and the y component of the net force also has to be equal to 0. All right, well, with that in place, let's go ahead and do a specific problem. The problem I have in mind here is to think about a three-way tug-of-war. So let's say we got 3 ropes that are all tied to a ring, and we have 3 people pulling on said ropes. So the ring is right there. So we've got a person here pulling on the rope, and as a result, the rope has 100 newtons of tension. And I'm calling it T1 just because there's 3 ropes, so I'm just calling them 1, 2, and 3. Similarly, got a person here who's also pulling on a rope, this rope here, with 100 newtons of force. We'll call that rope T2. And then we have a third person who over here who is pulling on a rope. And we don't know how hard they're pulling on the rope or at what angle. What we do know is that they are pulling on it in just such a way that nobody is winning the tug of war, which means that the ring isn't moving. So if you prefer, you can call this static equilibrium, but in any event, it means that the acceleration of the ring is 0. So let's go ahead and analyze the ring here. So we go ahead and we do a force identification diagram. We see T1 to the left, T2, T3. That's it. Just contact forces. All right. Let's go ahead and draw the corresponding free body diagram. So here we will have T1 acting left, T2 acting up, and again T3 acting down and to the right. And again, we don't know what the magnitude of T3 is equal to, and we don't know what the angle is with respect to the horizontal. Now, whenever you are looking at a Newton's second law situation, you are free to choose the coordinate system. In this case here, the up, down, right, left choice makes the most sense. And this is just because it minimizes taking components. T1 lies purely along X, T2 lies purely along Y. It makes the component taking easier. So then that just leaves us with taking components for the third force, T3. So we'll call this piece here T3X. That piece there, T3Y. All right, so with all that in place, so we can start by saying F net equals MA. Since we're in equilibrium, that means the net force is 0. Now there are 3 forces pulling on my object. So just writing this as a vector sum, this is T1 plus T2 plus T3 equals 0. Now from here, we can start to break this apart by looking at this in the land of X and the land of Y. So, and again, these will give us separate bits of information. So in the land of X, we can say that this will be equal to the sum of the X components of the forces. So T1X plus T2X plus T3X equals 0. Now let's go ahead and express that more carefully for this particular situation. T1 points purely to the left. So the X component T1 will be the entire magnitude of T1, but since it's pointing to the left, I'll have to put a minus sign in front to take care of the direction. So I write minus T1. T2 points purely in the Y direction. It has no piece in X. So the X component of T2 is just 0. So the only one that is going to give us any heartburn here is going to be finding T3X. T3X is, first off, it's plus because we are pointing to the right. And how much of it is pointing to the right? Well, this is the adjacent to my angle, and T3 is my hypotenuse. So if I remember SOHCAHTOA, that means that T3X would be T3 cosine theta. And that equals 0. Okay. Now let's also go ahead and write our system from the land of Y. We can start by taking the Y components of this. So this will be T1Y plus T2Y plus T3Y equals 0. All right. So Y doesn't have any component in the, or T1 doesn't have any component in the Y direction. It's acting purely in X. So T1Y is 0. T2 acts purely in the y direction, and it's the plus y direction, so we can just write plus T2. Remember, the magnitudes are always positive quantities. T3, well, the y part of it acts down, so anything that's down-ish, we need to put in a minus sign. And let's see, this is the opposite to our angle, and T3 is our hypotenuse. So SOHCAHTOA, sine is opposite over hypotenuse, so this will be minus T3 sine theta. And that also equals 0. Okay then. So we've got two unknowns. My unknowns are T3 and theta. I know T1 and T2. They're both 100 newtons. So the usual recipe is to solve one of these for, say, T3, plug into the other one and eliminate. So let's go ahead and do that here. So we'll start with what I have from the land of x. Doing that, I can rearrange. I'll have T3 cosine theta equals T1. So that'll give me that T3 is equal to T1 over the cosine of theta. Now the trick is to take our solution for T3 and stick it into the other equation. That'll make T3 go away, and we'll just be left with something with a theta in it. So we'll go ahead and make that substitution. So here we are now taking this bit with that substitution. So this will be 0 plus T2 minus, well, T3 is T1 over cosine theta times the sine of theta equals 0. Okay, so sine over cosine is tangent, so we can do that. And we're trying to solve for theta, so we can rewrite as T1 tan theta equals T2, tangent of theta equals T2 over T1. All right, now we need to get theta all by itself. So the trick here is we need to take the arctangent of both sides. So the symbol for arctangent is written like tan to the negative 1, but this isn't like 1 over or anything like this. This is the inverse function. You put in a number, it spits out the angle for which the tangent would give you that number. And of course you got to do the same thing on both sides. Well, the arctangent of the tangent is just the angle. So we get that the angle will be the arctangent of T2 over T1. Okay. So that gives us the arctangent of 100 newtons over 100 newtons. And it's a good thing that the newtons cancel. This is because with any kind of a trig function, the argument better not have any units, because it doesn't make sense to talk about something like the arctangent of newtons. So this will be the arctangent of 100 over 100, which is the arctangent of 1. Putting that in your calculator, you'll get that it's 45 degrees. Okay, so now that we got that, we can go back to what we found here. Let me just star that. And we can take this solution for T3. Now that we've got the angle, we know T1, we can find T3. So just copying it down over here, we have T3 equals T1 over the cosine of theta equals 100 newtons over the cosine of 45 degrees is 141 newtons, which is more than 100, so that makes sense. And it's less than 200, which makes sense too, because 200 would be what you'd have to do if the two ropes were parallel to each other, T1 and T2. Here, though, because these people are pulling somewhat helping each other, but also somewhat at cross purposes, this person doesn't have to pull as much as 200 because they're partially working against each other. Okay. So that's one example. And this is probably about as tricky as it gets when you're having to pull out an angle. It's pretty much unavoidable that you'll have to use some inverse trig relations there. But let's go take a look at another situation. And this one, we won't have to do that. So remember a few videos ago, you were taking a ride up a repurposed landfill that got turned into a ski resort. Let's say that this particular ski hill has a pretty sporty angle of 37 degrees, and I only choose that just because it's the interior angle of a 3, 4, 5 right triangle, which makes it relatively straightforward to remember what the sine, cosine, and tangent are. So after your journey up the cable lift in the previous video, now you're skiing down. There you go. And somehow you still have your hat on, despite the fact that you're going down at 60 kilometers per hour. How that hat is still on there, I have no clue. Must be an incredibly powerful headband. And you're going down there uniformly at 60 kilometers per hour. Now, I'm sure your mass isn't 100 kilograms, but let's just say our skier has a mass of 100 kilograms, just to have a nice round number to work with. All right, so what forces are acting on our skier? Well, we can start by drawing a force identification diagram. The circle cuts through the snowpack, so that means that there is a normal force and a force of kinetic friction. Here it's kinetic because the skier and the snowpack are moving with respect to each other. The skier is sliding down the mountain. And that's it. That's the only surface the circle cuts through. Then we look for long-range forces, and it's just the usual suspect of gravity. Okay. So what we're going to want to know is what is the force of kinetic friction equal to, and what is the normal force equal to. Now, this may seem like a bit of a mess, but it turns out it isn't awful, because the key word here is that you are going down uniformly. Uniform motion, remember, means constant velocity, or importantly for us, that the acceleration is 0. So even though the skier is moving down the mountain, this is an equilibrium situation. If you prefer, you can call it dynamic equilibrium, but again, that's just a matter of taste. All right. Now, at this point, I want to introduce what I like to call the first law of inclined planes. And that is, you should almost always choose your coordinate system so that it's parallel, so that the x-axis is parallel to the inclined plane. We call these inclined plane problems. It turns out that most of the forces, if you do this, will just neatly fall on the coordinate axes. The math generally tends to be a lot easier. You could make other choices, but if you do, the math will be a lot uglier, and it's a lot easier to end up chasing your own tail. This also brings up what I like to call the second law of inclined planes, which is that this angle here, the angle of the ramp, is also this angle right here. This angle with the vertical and the y-axis is also theta. You can prove this by doing some geometry, but I'm perfectly happy if you just call that the second law of inclined planes. In the first law of inclined planes, I did put in a caveat of saying usually you want to choose the x-axis to be parallel to the ramp. I have only ever encountered one problem in my career where you did not want to make that choice. It was a fairly complicated problem in electricity and magnetism, and it turned out there it made more sense to align the an axis with the magnetic field in the problem. But that's literally, out of lots and lots of these problems I've looked at, that's literally the only time I have ever seen a problem where it didn't make sense to tilt the coordinate system. So for our purposes, your first instinct should be to tilt the coordinate system to match the ramp. Okay, well, let's go ahead and draw a free body diagram. So again, here we look and we see, oh, we've got the normal force, and that will be perpendicular to the surface. So it'll be along this y-axis here. And friction is parallel to the surface, and since the skier is going down the hill, friction always opposes the motion. That means friction will be up the hill. And the only other force we have left is the force of gravity, which that always acts straight down. All right, let's draw our coordinate system back in. Oops. Let's do a better job of drawing our, doggone it. Let's try again to draw our coordinate system back in. There we go. So we're going to make this the plus y direction. Doggone it. There we go. And that's the plus x direction. All right. So with this choice, and this is why you always want to tilt your coordinate system, with this choice, the normal force is aligned in the y-axis, the force of kinetic friction is aligned in the x-axis. You don't have to take any components of those. And so that's 2 out of the 3 forces you don't have to take any components for. So that's why you want to tilt the coordinates. Now you do have to be careful when you are taking the components of gravity here. When you project back, you have to make sure you are going in perpendicular to the y-axis, or if you prefer, parallel to the x-axis. That's the same difference. So this will give you FGX, FGY. So don't go straight back. Go parallel to the axis to land parallel to the x-axis to land perpendicular onto the y-axis. If it helps you, a trick that you can do for a problem like this, and I'm just going to put this kind of as a parenthetical, when it comes to taking the counts, if you want to then just re-rotate the whole system so that you have, so you can take the whole picture and rotate it. This is much easier to do when it's not on a computer monitor. You can literally, if you're doing this on a piece of paper, you can just literally rotate the paper through the angle after you've drawn the free body diagram to get something like this. And then that will make it easier for you to pull off the X and the Y components of gravity if you prefer to do it that way. Myself, I always just found it reasonably intuitive to just go back parallel to the x-axis to land on the y perpendicular. But if that's giving you troubles, like I say, I can't do it on the computer monitor, but if you're doing this on a piece of paper, after you draw the free body diagram like this, just literally rotate the entire sheet of paper until it looks like this. And then it might be a little easier for you to take the components. Okay, however you do that, let's start expressing Newton's second law here. So F net equals ma, and the acceleration is 0. We've got three forces: the normal force, kinetic friction, and gravity. And as a vector sum, they have to add up to 0. Okay, so now here we can go to the land of x and the land of y and take the components of these. So this will be nx plus fkx plus fgx equals 0 over here in the land of x. Okay, so if I look here, the normal force is purely along y. It's not along x at all. So the x component is 0. For kinetic friction, it's purely along the x-axis. It's not along the y-axis at all. Now, it's pointing in the negative x direction, so we have to write minus fk. Then lastly, same deal here. This angle is the same angle as the angle of the ramp by the second law of inclined planes. And so FGX here, this is the opposite. FG is the hypotenuse. SOHCAHTOA, that means we need the sign here. And since it's pointing to the right-ish, that's going to give us a plus sign. So plus FG sine theta, that equals 0. Okay, now let's go to the land of y and do the same thing. So ny plus fky plus fgy equals 0. Well, the normal force is entirely along y, and it's acting in the plus y direction, so we can just write plus ny. Force of kinetic friction is entirely along x. There's none of it along y. So for the y component, we can just write plus 0. And then for FGY, okay, it's acting down-ish, so that gets us a minus sign. I need this piece here, which is the adjacent, so SOHCAHTOA. It's going to be cosine adjacent over FG is my hypotenuse. So that will give me FG cosine theta equals 0. Okay, now I know theta. I'm trying to, sorry, not ny anymore, just n. So I know theta, and I can figure out the force of gravity because I know the mass of the skier. I'm just solving for fk and n. Okay, so let's do that. So over here, this one's going to give me fk equals fg sine theta, and the force of gravity is mg, so we have mg sine theta. So for our skier, this will be 100 kilograms, 9.8 newtons per kilogram, sine of 37 degrees. That works out to be 590 newtons. Okay, over here I can solve for the normal force. The normal force will equal Fg cosine theta. So that's mg cosine theta. So, oops, that'll give me 100 kilograms times 9.8 newtons per kilogram times the cosine of 37 degrees. That works out to be 783 newtons. Now, both of these numbers are less than 980 newtons, which is the force of gravity on our skier. They're both bigger than 0, so this seems reasonable. Again, this is kind of like our tug-of-war situation where the other two ropes both had forces less than, where the sum of the two was less than the other one, was more than the other one. So that all works out and makes sense. Okay, in the next video, we will take a look at what happens when the acceleration is non-zero, what we call a dynamic situation. So catch you in the next video.